In an earlier discussion, I had a conversation with you about descriptive statistics, where we describe the data that we have in hand. And usually we talk about that data as being our sample. That's the data that we've collected, and now we want to describe it. The first option for describing data are going to be graphical techniques. Different types of graphs that will visually display what the data looks like. Another type of analysis or description of data that we'll talk about are numerical descriptions, and I'll cover that in a later topics. But in this video, what I want to do is talk to you about the different graphs and options. And I'm not going to cover all the options, just some ones we're going to see this semester and that you guys should be comfortable with taking a look at, creating in Excel, and I'll have you do some of that for me in your projects this semester. But more likely than either of those is I want you to be able to look at a graphical description of data and make some intelligent statements about it, answer some questions about it. So the first thing we want to talk about is the goal. We want to summarize the data visually. We want to take a look at a picture. Sometimes it's said a picture is worth 1,000 words. Well, in data, I don't know how many words I'd put to it, but you can get a lot of information just by looking at what the data visually appears like. And the type of graph that we're going to use, the type of graphical technique, is going to depend on the type of data. And again, in an earlier discussion, I talked about two main types of data. We've talked about the numbers, which we call quantitative data, and we've talked about the categories, which we call categorical or qualitative data. And I'll use those probably interchangeable throughout the semester. So let's start with our qualitative data. So to begin with, any kind of qualitative data, and this is going to be true for quantitative data as well, we need a frequency distribution. And a frequency distribution, we use lots of terminology in statistics, but a frequency distribution is just a table, a tabular summary of the data showing the various categories possible and the number of observations in each of those categories. So if I go and I take a look at students and I ask you, what's your political affiliation? Are you a Democrat? Are you a Republican? Are you a Libertarian? Are you part of the Green Party? And maybe I list 6 or 7 different political affiliations, and then I'll have another category, and I just take maybe I sample 300 students and I ask, which of these categories do you fall into? And maybe one of the categories, I guess, for political affiliation would be none. And I just count up the number of observations in each of those categories. That would be called a tabular summary. And here I have one for you. There's a data set, and it's called hotel ratings. And the hotel ratings data set consists of 649 different ratings of hotels. And the ratings were: this experience was excellent, very good, average, poor, terrible. And you can see the count, the number of, and that's a pivot table that I'm presenting to you here that I created in Excel for the different ratings that were found in this particular sample of 649 hotels. See, 187 said excellent, 252 said very good, 107 were average, 62 were poor, and then those 41 terrible. I was going to say those poor, terrible responses, but that's poor usage of the word. That's what's called a frequency distribution. Now, instead of the count, sometimes I can give you the percentage of the results. So 187 out of 649, that would be the percentage of excellent, and I happen to have a calculator in my hand. That'd be 28.81%, so 0.2881 or 28.81. If I presented the data that way, that would be called a relative frequency or percent frequency, a couple different words you can use. So the graphs begin with this little table, and we have a couple different graphs that we typically use when we're talking about qualitative data, when we're working with. And again, the qualitative or the categorical data are the categories: the excellent, the very good, the average, the poor, the terrible. And the bar length depends on the frequency or the relative frequency or the percent frequency of the various categories. And so I had Excel put together a bar graph. And so you can see in here that I have my 5 different categories, and the bars, how tall or short they are based on the ratings, the number of excellent ratings. There was 187, and so if I come in here, let's see if I can find my cursor. Here we go. This line right here, let's see if I can draw it. That line right there is 187. You can see it's in between the 150 and the 200. When you look at these bar graphs, it's hard to see exactly, like if I was to point out that bar, it sure looks like it's 250. It's 252, right? We need the actual frequency table to get the exact measurement. Now I can probably go into Excel and figure out an option where it'll tell you, and it'll actually write on top of the bar. It'll give you the value, and it would tell you this is 107. I can't ask specific questions. Like I can't ask you without the frequency table. I can't ask you how many very good responses there were and give you answers like 249, 250, 251, 252, because it's not that fine. You can't read the graph that closely. But what I could ask you, what's the most popular rating? And you'd be able to tell me very good. Or what's the least popular rating, or what's the rating with the fewest number of responses? And you'd be able to say terrible here. I should also mention, when Excel created this frequency distribution, and when it created the subsequent graphs, the ratings here were listed alphabetically. So average was first, and then excellent, and then poor, and then terrible, and then very good. And I had to figure out a way, and there's some fairly straightforward. You right click a lot in Excel to try to figure out how to change the order of the categories. But it made more sense for me, rather than do it alphabetically, it made more sense to go from the best rating to the worst rating, or vice versa. But that would be a good example of a bar graph. Another qualitative or categorical plot that we tend to use are pie charts. And again, it's based on the same information. We need a frequency or a relative frequency or a percent frequency distribution. But now the slices of the pie, how big or small the pie slice is or are determined by the frequencies or relative frequencies of the various categories. And so you can see in this particular case, I had Excel put in the actual numbers. So you can see the little scale over here, the legend, if you will. The excellents are the blues here. The very goods are the, what is that, like a burnt orange. The averages are the grays. The poors are the kind of goldish color. And then the terribles are more of the dark blue. And you can see that, again, you can see the biggest piece of the pie are the very goods. The smallest piece of the pie are the terribles. So you can make some general statements about these ratings based on these two types of graphs. So that's the two graphs, or those are the two graphs I want you to be familiar with when working with categorical or qualitative data, bar graphs and pie charts. Moving to quantitative data, and I wasn't expecting that bar graph to show up. My animations are poor again, but you have it all on your notes anyway. Again, you have a frequency distribution. The challenge now is, think about students. Think if I asked you your GPAs. And if you're sitting in a room of 120 students, let's say one of my live classes, for instance, and I ask people their GPAs, I'm going to get a host of numbers, and they're probably going to be somewhere between a low of around 2 and a high of 4.0. But let's say I focus on maybe the first row, and the first student I look at, they say their GPA is 3.51. I say, okay, good GPA, nice. The person sitting next to them is 3.52, and the person sitting next to them is 3.53. Here's what I will suggest to you. They're all relatively the same. They're all in that 3.5-ish range, right? When you're talking about GPAs, if I rounded them to 2 decimal places and you look around a room, because there's so many different outcomes, 3.53, 3.54, 3.56, 2.87, 2.88, you can't let each individual value represent its own bar in a bar graph when you're working with quantitative data. When you're working with qualitative data and you have classes, like different categories, excellent, very good, average, poor, terrible. There's delineations between the categories by the nature of the data you're collecting. With quantitative data, it doesn't work that way. You have a whole host of options that you can use or values you can see when you're working with quantitative data. And so what we do, rather than let each individual value represent its own category, for instance, we group similar observations together and we call them classes. So a tabular summary now of the data showing the various classes of data possible and the number of observations in each of these classes. Again, you can look at a quantitative or a frequency distribution, or you can look at it more on a percentage basis, which would be a relative frequency or percent frequency. And I've given you a frequency here. So rather than looking at, say I had 120 students in a classroom, rather than looking at each individual GPA, I would group maybe 2.0 to 2.5, 2.51 to 3.0, 3.01 to 3.5, 3.51 to 4.0. And there's a little bit of a science and an art. It's kind of a mixture between the two. And how do you determine what the classes are? How do I know how many classes? Generally, the larger number of data points that you have, the larger number of classes you want. But it takes some playing. Really what you're trying to do is get a picture where there's not just one observation in each class, but you don't want there only be 2 classes and you have 60 observations in each class. You want to spread the data out. And so there's a little give and take. It takes a little bit of finesse to come up with a good looking bar graph. but it's all based on the frequency distribution. In this particular example, this data set talks about best paying college degrees, and 20 different college degrees were listed in this particular data set. The percent increase in salary from last year to this year, and whatever year it was collected. And it was taking a look at the percent increase. And so you see there was one observation that had between a 40 and a 50% increase in the salary. Okay, so these are the best paying college degrees. There was 7 observations or 7 degrees that had a 70 to 80% increase in the salary year over year from one year to the next. 3 of the observations had between 80 and 90%. 3 had between 90 and 100% increase. 1 actually had between 100 and 110%. And there was 1 that was even greater than 110%. And so you see my 20 observations, and I have what, 1, 2, 3, 4, 5, 6, 7 different bars or classes, and you can see the bar graph that was created. So I could ask you, how many of the observations had more than a 90% increase? Now, one of the things you don't see when you look at this graph, or you can't tell when you're looking at this graph, what if somebody had exactly, or I shouldn't say somebody, I should say, what if one of the degrees had exactly a 90% increase in salary? Which bar would they be in? And here's an interesting truth when it comes to bar graphs: you can't tell. You can't tell unless you go back to the actual data itself and take a look at the individual. When you look at these 3 observations, and where am I at here? When you look at these 3 observations right here and those 3 observations right there, you'd have to actually go to the data and see, well, okay, how many of them, if there was one of the values that was 90, how many more were between 80 and 90? How many more were between 90 and 100? You'd be able to tell them where the 90 was placed. But without knowing, I can't tell you definitively if they're in the left-hand bar or the right-hand bar. And that's just nature of the beast. Different software programs handle it differently. But this is a good example of a bar graph. So we do bars, but we don't do it on individual values. You do it on the classes. Now, sometimes we'll call this, and depending who you talk to, I'm not going to be a stickler on any of the terminology, but for quantitative data, sometimes bar graphs are referred to as a histogram. Bar graphs, histograms, I'm going to let you use the terms interchangeably. A lot of software uses them interchangeably. But old school statisticians will be like, no, 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 it's a histogram when you're working with quantitative data. It's not a histogram when you're working with qualitative. So that's a term you'll see. That's one of the 2 quantitative graphs I want you to be able to work with. And again, you may need to do this for me in some of the work you're going to do this semester. But if I ask you to create a histogram, I'll give you the steps. I'll show you the steps. I'll create a video showing you how to work in Excel. And learning how to play around in Excel is probably a good skill for you guys to have. The second quantitative graph that we want to consider are called stem and leaf plots. And this is one of my favorite definitions of all time. Here's my definition of a stem and leaf plot. Ready? Data values are broken into stems and leaves. Now, if you know what a stem and leaf plot is, that makes sense to you. You're like, yes, nailed it. Perfect. But if you don't have any idea what a stem and leaf plot is, this definition doesn't help you at all. So it's usually best if I show you a couple examples. Here's some exercise times. And Excel does not give you an easy way of creating stem and leaf plots. This was using a software package from a prior semester. But I asked students, how many hours do you exercise per week? And the way to read the exercise times, you see all these numbers are sitting here. The way to read it, and again, let me see if I can find my cursor. Here we go, is right up here. The 5 and the 6, and so you got to find them right here down at the bottom. And usually when you look at the kind of the key up here, it's either going to point out the first observation at the very top or the bottom, and that's what it's done here. The 5 and the 6 represent 56. Somebody told me they exercise 56 hours per week. That crazy student said, I exercise 56 hours per week. So let me point out a couple other values here. This 5 that you see there, when you couple it with a 3, somebody told me they exercise 35 hours per week. And then you start looking at this. What the heck is this here? That's not somebody that said 256. That'd be crazy, right? That's one student who said 25 and another student who said 26. Look at the stem above it here. Look at all those. I have what? 1, 2, 3, 4, 5, 6. It looks like 7 different students told me they exercise 20 hours per week. A couple said 21, one said 22, and a couple said 24. And so you take a look at, if I grab this 7 right there, that's 07. That's somebody that said they exercise 7 hours per week. This little asterisk out here means there's a lot more observations out there. It didn't give me all of them. But that's where and I think you're probably seeing it now. You're saying, wait a second, it looks like the data values are broken into stems and leaves. If you said you exercise 18 hours per week, this would be you right there, right? The 1 and the 8. Let me show you another one here. Here's some GPAs. And so you can see here the 1 and the 7. There was a bunch of people that told me their GPAs were 1.7 for whatever reason. There were no 1.8s and 1.9, so you see a gap here. Likewise over here, nobody told me they exercise in the 40s or the lower 50s. And so you see this space. There's no leaves here. We leave that space in there so you start to get a feel for the shape of the data. Now let me go back. Let's see if I can go back. The shape. Here's a shape of the salary data. Again, let me find my cursor. You can see, look at this shape here. So like a big hump, and then as the percentages increase, it kind of gets lesser and lesser. When you look at the stem and leaf displays, when you look at exercise times, most of the exercise times are in here, and then it tails off really sharply. Most of the GPAs are over here. Look at all those 4.0s, and then it tails in the other direction. The data values are broken into stems and leaves. So the stem and the leaf, let me finish this before I go on to my next topic. The stem and leaf display are these two columns, the stems and the leaves. This column over here, this particular software program uses a weird word, depth. And you see it in both of them. Where am I at? Here I am. The depth here. This is a counting column. This counts up the number of observations. So what the depth column does, it says, look at this first stem. Look, there's 6 observations in that first stem. Then it goes to the second stem. Now you see there's no additional observations. There's a total of 6 in the first 2 stems. And I add this 0, the 2.0 here. So there's a 7th observation. And so each of these numbers is counting not what's in the stem, but what's in the stem and beyond. And it's actually doing that from both directions. There's 11 4.0s. There's 30 in the 3.8 and 3.9 rate. So there's a total of 41. It's counting from the edges of the data, or sometimes referred to as the distributions, towards the middle. And you guys probably know, and in another video, I'm going to talk about the center of the distribution. We're going to talk about the middle observation. That's referred to as the median. This particular package says, well, the middle observations found in here, there's a total of 33. That's what the parentheses are for. There's 33 in this particular stem. I don't know which way you're counting from. Sometimes it's helpful to use this counting column. Like if I ask you, how many of the GPAs are less than 2.6? So you can say, well, these guys are less than 2.6. Now you could count up the individual leaves, or you could look right here and see that there are 16 of them. How many of the students exercise 10 or more hours per week? Well, that's like everything here. There's 66 of those observations. That's what this number here tells me. And so that's how that depth or that counting column will be used. But the actual stem and leaf display itself are found in the stems and the leaves, those 2 columns. So both of these methods, the bar graph and the stem and leaf display, attempt to visualize and show you where the data falls. The only advantage of the stem and leaf plot are you have very specific information. Remember the problem we ran into with this guy? What do you do with the 90? Well, here, you see the actual data values. You don't lose. The individual data values are still there. And a lot of times what we're using these graphs for is trying to determine the shape of the distribution. And so there's 2 main shapes I want you to think about, and I'm actually going to break it into 3, but you'll see what I mean. There's symmetric, and in symmetric distributions, you guys know what symmetric curves look like. Now we're going to be using bar graphs or stem and leaf plots, but you have basically the 2 sides look pretty much the same. They're mirror images of one another. In skewed distributions, one of the tails is going to extend further than the other. Think about what did we just say? Let's go back here. Let's look at this one. When you say the salary percent increase, that's not symmetric. That's a little bit skewed to the right, right? The right-hand tail extends further. Let's take a look here. The exercise times, now that's kind of turned sideways. You want to think about it. You want to rotate this 90 degrees, but you want to kind of rotate it that way. What do I mean by that? Put the 0 values, the smaller numbers, on the left-hand side. Put the bigger values on the right-hand side. Can you see that this distribution looks very skewed to the right, right? And this one here, which I haven't shown you, this we have, again, turn it so that the smaller GPAs, the 1.7s, are on the left. The bigger GPAs are on the right. Put it on a number line. This one looks more like that. And so I'm going to put here A skewed left distribution, sometimes referred to as a skewed negative, has the long tail to the left. A skewed right distribution has a long tail to the right. Now I'm drawing pretty black and white type of pictures here, and what I mean by that is it's very symmetric in the first picture. It's very skewed left in the second picture. It's very skewed right in the third picture. Can you see how if I took this tail in the first picture and drew it, take it a little bit, at some point you start changing symmetric curves into skewed left, skewed right. So it's not always as easy to tell, but I want you to get a sense of what those shapes look like. Those shapes are going to help us when we try to describe where data falls, and that'll take place in a future topic. And so I'm about 20 minutes. I think is a good place to end this particular topic, looking at different ways of graphing quantitative and categorical data. So long.